Light is complicated enough to behave like both a particle and a wave. Here we're bending light without mirrors. To learn how this is possible, we'll use a model. Notice that these cars move straight down the hill. Watch what the soft carpet does to the path of the cars. When the wheels hit the slower medium, the cars are bent off course, just like the refracted light beam. Notice they resume in their original direction when they speed up, leaving the carpet. This is what happens to light. When it moves from air to water, it slows down and bends. From water to air, it speeds up again and bends back. The bending of light as it passes from one medium to another is called refraction. Light can also be refracted by a transparent, solid material. This is how a lens works. And by replacing the flat wedges with a lens, we focus the light. With more bending, the focal point moves closer to the lens.
Does light only reflect?
No, light also refracts.
What does refracted mean?
Well, Bianca, I think it's easiest to show you. Okay, Bianca, we need to put on some gloves and goggles because you're going to work with some liquid nitrogen.
We use these in science.
Good. It helps to be safe when you're doing experiments.
What's that stuff bubbling?
It's liquid nitrogen. We're going to use the vapor to explore reflection and refraction. So, Bianca, this is a laser, and I'm going to shine it on the gelatin. But first, I need to have you dim the lights. What I'm going to do now is shine it on the gelatin. Look closely and tell me what you see.
I see the light coming off into the gelatin. That must be reflection.
Right.
But the light is also being bent. Why is that?
Well, when light travels from one medium, such as air, to another medium, such as gelatin, its speed changes. And when the speed changes, the light bends, and we call that light refraction.
Does the speed of light speed up or slow down when it's going through the gelatin?
Well, because the gelatin is thicker than air, it slows down.
Sandy and Bud like to out simple versions of demonstrations they've seen in the science lab at school. The bright sun pouring in through a tiny hole in the tent provided a ray of light, and with a few simple gadgets, they could see how light behaves. A shiny piece of metal made a mirror. What happens when light bounces off a reflecting surface like this? They could see the angle of the reflected beam as the mirror was rotated. Sandy showed Bud the relation between the incoming light and the reflected. Regardless of the size of the angle, the law of reflection is the same. The angle of incidence, that is, the angle at which a ray strikes the surface, is equal to the angle of reflection, the angle at which it leaves. This principle is true not only for flat or plane mirrors, but also in a slightly different way with curved mirrors. At different parts of the curve, the rays are reflected at different angles. A concave mirror converges the ray, while a convex mirror spreads or diverges them. Sandy said he could always remember concave by thinking of a sort of a cave, hollow. Convex is the other way. These principles are used in the trick mirrors you often see in amusement parks. Bud makes a more practical use of a curved mirror when following his hobby of photography. The interior surface of this reflector is curved so that the light is directed toward the picture-taking area. Well, that's what happens when light is reflected from things. Now, what happens when light goes through things? Well, it appears to go right through this glass. Actually, however, while light is passing through glass, it slows down to about 2/3 of its normal speed. In the air again, it resumes. When the rays enter the glass at an angle, this slowing down and speeding up causes refraction. Rays that enter first slow down first, causing the beam to bend. They also leave the glass first and speed up first, causing the beam to bend back parallel to its original direction, but offset or shifted. When Sandy handed Bud a glass prism, he could see how the sloping sides changed the direction of the beam. Back in the boat, Bud could see refraction as he dipped an oar. Because light coming from the underwater parts of the oar is speeded up when it comes out, the rays are bent, and so make the oar appear to be bent.